Hi, good morning, and welcome to the Developer Zone webinar. So we like to do this every Thursday at approximately 8 a.m. Though we do tend to kind of go a bit early on our webinars these days because the days just get so busy with meetings. But let me go forward anyway with this webinar and say welcome to the webinar. So don't forget the ZP Academy. If you're looking for free advice on electrochemistry, there's a couple of free courses up on the Academy. So if you sign up, you can get access to those free courses on electrochemistry for biosensor developers. Don't forget, we do these webinars. So for example, this is just one of 4 free webinars that we do a week. And we do collaborations. We do have about 5 PhD students running at the moment. And we do offer jobs, and we do have our ZP Developer Zone, and we do have our workshops. So let me go forward with talking about these things. I will talk fast. We do have meetings. I do respect also your time, and I don't want to be inefficient with it. You will see links popping up in a minute. If any links, I've already put them underneath this video that's on YouTube as well. So you'll find those links in the description box on YouTube. Don't forget that we do have hands-on workshops, one running in Norway in November, one running in Coventry in November, one running in Coventry in December, and one running again in Norway in December. So we do have these workshops. All the questions that have come in today are sort of relevant to those workshops, because in those workshops we do talk about kind of electrochemistry, IVDs, that's in vitro diagnostics, also wearable sensors are all kind of covered in there. And it's not just talking, it's actually going into the lab and doing experiments, including experiments like ferricyanide, which is which is one of the things we cover today. Let me go forward a little bit quicker and say, we do have free webinars as well that are a little bit more in depth. So we do have one on data science. If you see again a link popping up, I've already put the links underneath the video. These are some free webinars that we have running at the end of November and December. We have one on Julie. Julie is a cloud data system or data management system that we have at ZP. There's a freemium version, and then there's also a premium version. It's really for uploading data, visualizing data. When I say data, I should really mean it's sort of tuned for electrochemistry mostly, and also for sharing data and also for processing data. We do have Sense It All as well. I'm noticing today that a couple of the users who have asked questions are kind of using these quite bulky potentiostats. So I really want to I'll just mention it a few times today that electrochemistry doesn't have to be bulky potentiostats. I think, in fact, if you're doing sensors like glucose and cyclic voltammetry on screen printed electrodes, honestly, reducing the potentiostat size moves you mentally closer to actually being able to make products. And we also have something, these live streaming webinars called Food Sense. So if you're a academic electrochemist and you really want to understand the real world implementation of electrochemistry into real products, then I would suggest that you attend this webinar. The link's there. You can find these webinars on our pages. In June 2024, we do also have a special conference running in the UK on the commercialization of electrochemical assays. We will have another conference in Norway in January 2025, which will be on precision agriculture. You can register now for the conference in June in the UK. I've already touched upon this, so I won't repeat. We do corporate workshops as well. I know that many of the questioners that have come in today are much more academic based, but we do go into companies and we do workshops where, for example, everyone gets to make a glucose sensor, everyone gets to test a glucose sensor by amperometry, talk about generation 1 glucose sensors, and we also talk about generation 2 glucose sensors as well. So questions today, what's wrong with my cyclic voltammetry? So somebody's got what they're terming a crossover in their cyclic voltammetry. There's nothing wrong with their cyclic voltammetry. I'll just explain why I think it's coming about and why you shouldn't really worry about it. Electrodes for microvolumes. So I don't know how I sort of figured this out, but I was thinking somebody was asking about they want a screen printed electrode with a gold electrode, a platinum electrode, and a silver chloride electrode, and I somehow figured out that they were doing it in microfluidics. So microfluidics / microvolumes, and I will discuss that today. And also question 3, la détection de glucose par SP 300. So this person's coming in for someone like Morocco, I think it was, and they're asking about the detection of glucose on an SP300 potentiostat. So I will touch upon that as well. So question number one, crossover in CV. So you can tell immediately that this person's using a CH Instruments potentiostat. I just think that CH Instruments potentiostats, they kind of, you know, they're rather large. They sort of tell the wrong story to people doing electrochemistry, but electrochemistry can be very kind of a very compact, elegant science. But they're using CH Instruments instrument, which is fine. I think their concern is this kind of crossover here. The first thing I want to say is when you see cyclic voltammetry, classical cyclic voltammetry in papers and textbooks, they're often showing you the second scan. The first scan is always the one with sort of these kind of anomalies in it. So when you see nice cyclic voltammetry, I suspect that this person, they've done one cyclic voltammogram, and in fact, if they did a second one, the second one would be wouldn't have this crossover phenomena. But I'll touch upon that a little bit more. I thought initially when I was looking at this that actually what's happening here is at minus 0.6 volts. Now I think they're on a carbon electrode, so it's a little bit harder to reduce oxygen on a carbon electrode as opposed to platinum or gold. So I thought, oh, okay, they're reducing oxygen, but I'm not super convinced that it is necessarily the reduction of oxygen. But first of all, this crossover, you won't see it on the second scan, and just know that many papers and textbooks, and I know I've already said it, they're not showing you the first scan, they're showing you the second scan. That's why I'm not super worried about it. Sometimes when we're doing this kind of work, and I think I've got a video later on where we actually start at minus 0.5 volts, but I've also seen some of your other data where you're actually doing it at minus 0.4 volts, and you still get this crossover. So that, you know, admittedly, I don't think that's going to solve your problem here. I just want to quickly say the reason that you get this crossover as well is you'll see me do a video in a bit where actually we start at 0 volts. So some potentiostats, including the CH Instruments, they may allow you to start at what's called open circuit potential. So when you start open circuit potential, you start in a place where everything is actually at equilibrium. So what you're doing is you're starting your experiment far away from equilibrium, and then you kind of you sort of scan up from there. There's nothing wrong with what you're doing, and if you want to stay this way and you want to report nice looking data, just report the second scan of the CV. But the open circuit potential for ferricyanide on a carbon electrode is approximately 0 volts when the reference electrode is silver chloride in PBS. I know that because I'll show you a video in a bit. So if you start at closer to 0 volts, you won't have this crossover effect, but you'll see that in one of my videos in a minute. There is a problem with these electrodes. These are not ZP electrodes, by the way. I must flag that up immediately. ZP is an unusual company that the biggest users of ZP electrodes, screen electrodes, is ZP. So we really watch the quality of these electrodes because we have to use them in our own products, etc. But the thing is, I noticed that the peak-to-peak separation is quite high, 450 millivolts. Which is a little problematic if you were trying to sort of report this in a paper, because you could be criticized by the reviewers. So the reason this is coming about is I'll sort of do I've got a few videos on this. This is not our electrode. I've obviously, you know, out of respect to the manufacturers, I've covered up the names. But what's going on here is the peak-to-peak separation, I think, is coming about because of there's too much resistance in these electrodes, and you can see it in when I look at this image. So this is I presume the counter electrode. This is a carbon pad, and this counter electrode is carbon. The first thing to say is, when you look at that electrode alone, carbon ink is the most resistive of the inks. So when I say that, I mean I'm thinking about platinum and gold, for example. Carbon inks can be hundreds of ohms to even kiloohms in some screen printed electrodes, whereas platinum and gold can be, you know, just a few ohms of resistance. So I got a suspicion the counter electrode material is carbon all the way along this track, so that's actually quite a lot of resistance. Also, that counter electrode is fairly small compared to that working electrode, and I also noticed that the working electrode is exactly the same. Actually, it's also carbon, probably all the way along that length. Now, I suspect with a reference electrode that it's not a big issue because there's not current running through it. So I'll skip that comment on the reference electrode. But I suspect that your cyclic voltammetry is distorted because of the internal resistances of the screen printed electrodes that you are using. If you look at ZP's sort of equivalent to this one, you'll see that, for example, here's our counter electrode. That pad there is silver, or silver chloride, and then along there is a lot of silver chloride. You can see that we're trying to ensure that we've reduced the resistance as much as possible. There's good reasons why we don't bring it all to the end here, but you can see that we're taking efforts to decrease the resistance along that track. It's also quite, on this particular electrode, this carbon 501, that's quite a big counter electrode, and that helps reduce the charge transfer resistance at that counter electrode. You'll see our working electrode has a similar kind of design as well, where we're really trying to take care of that resistance along that pad, and it really leads to a, dare I say, a high quality product. And I have linked to that here as well. So I think you're suffering distortion due to internal resistances. I know it's not your question. Your question's about crossover, but 450 millivolts peak-to-peak separation is quite a lot, and it could be sort of problematic. And it's just basically because of the way the electrode is constructed. We do have these platinum 501s as well, if platinum is your material of choice. This will come up later on in question 2, but just out of interest, on the platinum 501s, we have the counter electrode of silver chloride. It's actually a good choice, that is. Now, admittedly on the carbon, it's carbon, but on the platinum 501s, it's silver chloride, and I'll touch upon that in a minute as well. So I would absolutely suggest that you will get better quality cyclic voltammograms if you want to use carbon or platinum by using these 501 series. Something that just occurred to me as well is, obviously this is not the potentiostat you're using CH Instruments, but this is a fairly a small, nice potentiostat with the EIS functionality. There's also a series of electrodes, I will touch upon this in question 2 as well, called the hypervalue carbon electrodes, and they work really well, and we use them a lot in our products. Just a cable that goes with that potentiostat as well, but this is what I really wanted to get to as well. We also have these nice connectors. Your distortion on your voltammogram could also be coming about because of there's some sort of high impedance connection issue between your screen printed electrodes and your potentiostat. That's why we kind of, we do make sure that we do have a very nice connector. And I think CH Instruments is using either a 2mm banana plug, maybe 4mm, but I think it's 2mm, and we do have a connector for that to go between our screen printed electrodes and CH Instruments as well. Just back to your question about crossover. So this is a video, and I've also got a link that will pop up in a minute. It's a really old version of the Anapot potentiostat. And in this video, I'm just playing it now, and I can just vaguely, I can see it now. I can see that the beginning voltage here is 0 volts. The first vertex was 0.9 volts, which is quite high. I don't know why I went up to 0.9 volts. Now, this work was done a long time ago. I wouldn't do this work like these days, but we went up to 0.9 volts. We came back to minus 0.5 volts. We had a stepping potential of 0.01 volts and a scan rate of 0.1 volts. So it's quite a high scan rate. I should have checked the scan rate on your CVs as well. The reason I bring it up is because when we do this experiment, if you've just got ferricyanide, if you start off at 0 volts and scan in a, let's say, positive direction, it gets a bit confusing because sometimes the American system, you think of voltages the other way around. But because I'm using ferrocyanide, I do get the immediate oxidation of ferrocyanide to ferricyanide. If you just got ferricyanide in there, you may just get very flat here because you're already in the ferricyanide state. But here's my reduction. Now what's interesting is it kind of equilibrates itself on this initial part of the scan, and then we get our reduction. Notice the way that almost comes back to the same thing. So I don't have the same kind of crossover, let's say, of view. On the second scan, everything's equilibrated, so we get the oxidation of ferrocyanide to ferricyanide. And now we get the reduction of ferricyanide to ferrocyanide. And just notice the way the reduction curves are on top of each other. And, you know, it really follows itself. I'm just going to let it get. And then when you get to the end, now what happens in, I say, a lot of scientific papers, and I'll pause it. Whoops, a daisy. I should have paused it there. They actually don't report the second scan. They only report the second scan. They don't show you the first scan. So your concern about crossover is not I'm not so concerned for you, because actually you can just report the second scan. I think you have a problem with resistance, internal resistances along those electrodes. And I can see it there now. It's sort of the second scan is, you know, the perfect, let's say, I don't want to say duck shape because everyone uses that kind of that term, but you know, it's pretty perfect and you could report on that. So the crossover doesn't concern me. If you start at closer to 0 volts, you'll probably find that that crossover doesn't take place. And if you report only the second scan anyway, it'll all sort of go away for you. And here's a link to that video. You'll find that video and then link to also underneath this webinar as well. Because this a little bit concerned me. I mean, this is really distorted. If this is, you know, ferricyanide, I mean, you've got your crossover, which is your concern, but it's very distorted. And I got a suspicion it's sort of the internal resistances on that screen printed electrode. So it's not a ZP1. Be careful with it. I know you're using a CH Instruments. And, you know, I'm just saying, you know, these days, the, you know, potentiostats have got a lot smaller. So just one comment here as well is be careful sometimes with these USB powered potentiostats, because they're a little bit lower power. There's something called the compliance voltage. With the silver chloride counter electrodes that ZP often employs, they work quite well with these USB power potentiostats because the silver chloride means that the compliance voltage is a lot lower. But when you have something like a carbon sometimes, especially I would say carbon counter electrodes that are quite small, you can have quite a high charge transfer resistance at those electrodes, at those counter electrodes, and therefore the compliance voltage has to be higher. And the these USB potentiostats literally can't provide the power. So be a little bit careful. For just general lab use, I would use something more like an Anapot. And I've actually linked to it here as well. I also just, I've linked to something called the Sense It All webinars earlier on. Just come to one of those webinars because I really want you to get a sense of, you know, how to translate lab research into products. And I would say that, you know, that kind of translation probably starts at least with good quality reproducible screen printed electrodes. So hopefully you'll translate onto our platform. Question number 2. This came about because we had an inquiry that kind of said, I think one of the questions was, can I have a gold working electrode, a platinum counter electrode, and a silver chloride reference electrode? The first thing to say is when you have 3 materials like that, there's very few screen printed electrodes on the market like that. And when people do manufacture those, they're manufacturing them in quite low volume. So be careful, because when they're manufacturing low volume, it means that they're not really manufacturing. They're doing what's called batch manufacturing. So the reproducibility from batch to batch can be quite variable. The reason it's not always a good idea to have platinum and gold are intrinsically expensive, which is, you know, fine. You know, I try to encourage everyone onto carbon these days. But you're adding an extra manufacturing step because we have to print the silver chloride, the gold, the platinum, and the dielectric. That's 4 steps. If you just had 2 electrodes that were, 2 of the electrodes were the same, then you'd have the gold, the silver chloride, and the dielectric. That's 3 steps. So you're essentially adding an extra step into that, and you're adding an extra degree of complexity and expense. And later on, if you really want to kind of scale this up and turn it into a product, you've embedded this cost that I really don't think was gaining you anything. I think sometimes people ask for a platinum counter electrode because, you know, when they're thinking about big electroanalytical cells, you know, they'll have a working electrode, a silver chloride reference electrode, and a platinum gauze. So that's where this kind of desire for sometimes having platinum as the counter electrode comes from. But it's really just a tradition that's coming from the macro cells. So my kind of recommendation to these people is, first of all, always try and figure out your chemistry to work on carbon. We can sell 300 carbon electrodes for 250 euros. It's a massive difference in price. I can't do this with gold and platinum. The gold and platinum gold is 32,000 times more expensive than carbon. It's just, and platinum is even worse. So we do have some carbon electrodes, some platinum electrodes that I recommend. This carbon electrode has a working electrode that's carbon, a counter electrode that's carbon, and a silver chloride reference. This platinum has a platinum working electrode, a silver chloride counter, which can be beneficial to people working in microvolumes and microfluidics, and a silver chloride reference. We do have this hyper value, which has a carbon working, a silver chloride reference, and a silver chloride counter. We have a platinum equivalent, which is platinum working, silver chloride reference, and silver chloride counter. We also have a gold hyper value, which is gold working, silver chloride reference, and silver chloride counter. I've got links to all this. I've put the links also underneath the video as well, so you'll be able to find those. My recommendation is always try to just go for carbon. I think we're selling the carbon electrodes for less than €1 each, whereas we're selling the gold, for example, are about €6.50 each. And it's not because it's just the price of gold. And at ZP, we're a little bit different because we're all the time thinking about, even though you're doing lab work, one day somebody might want to commercialize this, and commercializing off gold or platinum is a bit of a problem. But I can understand that sometimes you need it, and so my recommendations are, there's a range here, and we try to keep the cost down as much as we can. As I say, I think sometimes when this request for mixed electrodes comes about, it's because people are used to this kind of large reactor or vessel, and there, it's typical that you may put a platinum gauze electrode in there, but bringing that kind of thinking across the screen with electrodes is not always super beneficial. There is something important about our silver chloride electrodes, and this is something I've spotted sort of 20 years ago. People never talk about this. I think this is probably the only place you'll actually find everyone ever talking about this. But you have a counter electrode and you have a working electrode. Now, let's say at your working electrodes, you're doing you're doing a piece of electrochemistry. The question is, what are you doing on your counter electrode? You could be producing protons, which is changing the pH, which becomes more important in the micro reactors or microvolumes or microfluidics. It doesn't matter in those batch reactors, but the question that nobody answers is, what are you doing on your counter electrode? So if it was platinum, you could be producing protons, you could be producing hydroxides, which is making it more alkali, or you could be producing sometimes things like hydrogen peroxide. So what happens in these microvolumes, or what can happen, is that for example, you're oxidizing in a working electrode, you're having to do some sort of reduction on your counter electrode, and that material on your counter electrode can end up diffusing across your working electrode, where it's actually reoxidized. So this is basically a chemical crosstalk. That oxidized material then diffuses around and actually can get back to the counter electrode, which then it's reduced, which then it means it diffuses back to the working electrode where it's oxidized. And you've actually got a crosstalk, a chemical crosstalk, where the working electrode and counter electrode, one's doing reduction, the other one's doing oxygen. Material produced from one electrode is diffusing to the other electrode, where it's then converted, which then drives the electrode even harder, and you've actually got a cross talk. What this phenomenon looks like is you can end up with a, if it was amperometry, you can end up with this phenomenon where you've got a chronoamperometry experiment. I'm showing it like a Cottrell, and then after some seconds, actually the current starts coming up, and this is because you've got crosstalk between the counter electrode and working electrode. Never happens in larger glass reactors, but it does happen in microfluidic devices. But at ZP, we make many of our counter electrodes silver chloride because I think we're one of the few companies that actually produces screen-printed electrodes that's also very steeped in vitro diagnostics. And so we do understand this phenomena. We don't want crosstalk in our in vitro diagnostics. I mean, in an in vitro diagnostic, you take a drop of blood, you do an analysis on it. Well, it's a small volume, and you can end up with this kind of crosstalk. So we make our electrode silver chloride because if we're doing reduction at the counter electrode, then silver chloride becomes silver. Silver's insoluble, it stays in place, it doesn't diffuse across to the counter electrode and cause crosstalk. If we're doing oxidation at the counter electrode, then silver oxidizes the silver chloride. Again, it's insoluble, it doesn't diffuse across to the working electrode and cause this electrochemical crosstalk. So that's when I make my recommendations. I'm making my recommendations based on what we have, on our experience, and also, I should say, and on this experience as well. So when we replace that, let's say it was a platinum or gold counter electrode with, or carbon counter electrode, sometimes with silver chloride, you can get this phenomenon. So my recommendation is I've listed out quite a few screen printed electrodes. Maybe I think try those 501s and those hypervalue electrodes would be my recommendation. The last thing is compliance voltage. So this is not, again, our electrode, but when I look at this electrode, it has quite a small carbon counter electrode. This means that that potentiostat is having to do quite a lot of work in order to apply a potential at the working electrode. So let me say that. So you've got your reference electrode here, you've got your working electrode here, and you may set a potential of between the working and reference of 0.5 volts. Now what the potentiostat may be doing is actually setting quite a high compliance voltage on the counter electrode of something like -1 volts to support the amount of electrochemistry happening on the working electrode. But when you, as you know, as I've already mentioned, many of the counter electrodes are ZP are silver chloride. So when we do that, that compliance voltage for otherwise the same scenario would actually go down to 0 volts. And, you know, that's again direct experience. And it's because it's not always easy to do. If you're oxidizing on a carbon electrode, you've got to ask yourself, what am I doing on my counter electrode? It's also carbon. Well, you're probably reducing either oxygen or doing the electrolysis of water, which are both going to take quite a lot of potential. But of course, if you are oxidizing on the carbon working electrode and the reference electrode is silver chloride, then you're reducing silver chloride to silver, which is much easier to do, and therefore the compliance voltage is much lower. So I would my tendency would be to recommend the hypervalue carbon, platinum or gold for working with microvolumes. And so I have run through these electrodes. I suppose it's the last three that I would, well, actually the 501 platinum here also has a counter electrode that is silver chloride. But I think because of the cost, I'd also try out the 501 carbon as well, because that 501 carbon's got quite a large counter electrode, which will probably mean that the compliance voltage can be lower because there's so much surface area there on which we can do electrochemistry. So question number 3 is somebody's trying to do a chronoamperometric experiment of glucose on an SP300. SP300 is a pretty large potentiostat from biologics. I've owned Auto Labs in my time. I've owned CH Instruments in my time. I've owned biologics in my time. Obviously today I'm very biased because, you know, I run Zimmer Peacock, so I'm obviously very interested in supporting our potentiostats. But I mean, glucose, I'm really surprised because, to be honest with you, making a glucose sensor by electrochemistry is really quite a straightforward, I want to say thing. You know, we do this quite a lot. We do, you know, in our workshops, everyone comes in and we take the platinum electrodes and we kind of immobilize the glucose oxidase on top of them. We'll put a barrier layer on top of them, you know, and then everyone kind of, you know, goes into the lab and we start testing with glucose and we get, you know, quite a nice signal. Of course, it's because glucose is reacting with the enzyme, generating hydrogen peroxide, and we're using a potential of about 650 millivolts. So now I remember why I put this slide up there is, first of all, what potential are you actually applying? Maybe I should say to this person, and I want to say as well, don't worry, my French is not so bad, so if you want to write to me in French, don't worry about it. I will, je peux comprendre le français. So don't worry about writing to me in French. First of all, what potential are you using? It's probably worth sending me data, to be honest with you, because I realize then with data I can actually be a bit more analytical about it. But first thing is, what potential are you actually using is the question. And then, you know, when we're testing these kind of things, you know, we have our glucose sensor, you know, in a beaker. We start adding in glucose solutions, you know, and this is running at chronoamperometry at 650 millivolts, and the signal increases proportionally. Now I have a video here, and I've also got a link to the video as well, because we went into the lab a while ago, and the wire electrode that we show in this video is definitely something that we are you can find it on our website. You know, it's one of our actual products, and in here I can see them. She's actually using a potential of 0.5 volts, but I think it's better to use 650 millivolts or 0.65 volts. I can see that really, I mean, it's just, she's obviously running chronoamperometry, and just checking what she's doing with the save rate, but we generally just save at 1 a second. There's no big deal. At which point now Lynn's going to start adding in glucose. So she's got the sensors. By the way, I do put the video underneath, a link to the video as well. And I can see here that she's adding glucose, and every time she adds glucose, the signal increases proportionally. So now I can see that Lynn's adding more glucose. So I'm a little bit surprised that you're struggling with chronoamperometry. Maybe send me the data, because we go in that, you know, if we get somebody into one of our workshops, you know, we may do, you know, talking for 45 minutes, but 45 minutes later in the lab making a glucose sensor. So, you know, I think we've never not had a success of doing that. So hopefully this video may also guide you as well. So I say you thank you, but let me just do a quick summary. So the first person had a problem with crossover on their cyclic voltammetry. Don't worry, everyone gets it. When you see that beautiful data in papers, they're often showing you the second scan. In your particular case, if you want to reduce that crosstalk, maybe start at 0 volts. But because you're probably just in a ferricyanide solution, it's not a mixture of ferri and ferrocyanide. Just know on your first scan, if you scan in a positive direction, you will get no oxidation because it's already ferricyanide. So you could scan in a negative direction, reduce that ferricyanide to ferrocyanide, and then scan back to positive, and so you've got a sort of now a small reservoir of ferrocyanide that will oxidize to ferricyanide. But don't worry about this cross scan, to be honest with you. I think you've got more of a problem that actually your voltammetry is very distorted because of the impedances inherent in those screen printed electrodes. Obviously, you know, I'm biased. I would recommend our electrodes. They give really quite nice data. The person who's trying to do electrochemistry in microvolumes and maybe even microfluidics, I think the carbon 501 is worth investigating. I think the hypervalue carbon electrode is worth investigating. The hypervalue platinum electrode is worth investigating. And the hypervalue gold electrode is worth investigating. And then the person with the chronoamperometry SP300 problems, I'd probably send me some data, but the video I'm also shared will actually be a useful guide for you as well. So as I say, we do this once a week. We answer all technical questions that have come in during the week. So if you've got any technical questions, again, don't hesitate to reach out to us at ZP. Okay, thanks very much.